Welcome to this explainer. Today, we're going to treat your LTE network exactly like a patient. If you're an engineer dealing with lagging speeds and just generally poor throughput, we're going to help you diagnose the root causes of those issues by mastering one absolutely vital network metric, the Channel Quality Indicator, or CQI.
So, you know the feeling. You might be wondering, why do LTE speeds just suddenly drop for no apparent reason? Well, when a user experiences a sudden, super frustrating plummet in download speeds, it's almost always because their device is reporting a poor CQI to the network. Honestly, it's often the silent bottleneck of network performance.
To fix this, we're going to walk through a pretty structured agenda today. We'll hit CQI basics, reporting mechanisms, key monitoring metrics, our 5 pillars of optimization, and finally wrap up with some real-world success cases. Let's just dive right in.
Okay, Section 1, CQI Basics, where we define our network vitals. Let's start with the absolute fundamentals of what CQI actually is and how it totally dictates your network's behavior.
At its core, the channel quality indicator is a metric reported by the user equipment, the UE, back to the cell tower, the E node B. It indicates the downlink channel quality so the network can select the most optimal modulation and coding scheme. The golden rule here is keeping the block error rate under 10%. Basically, think of CQI as a constant report card that the student, your phone, hands to the teacher, the tower, saying exactly how well it can hear the lesson.
When you look at how the CQI index maps directly to modulation, the impact is huge. Higher CQI indexes, those hitting from 10 to 15, allow the network to leap from basic QPSK modulation all the way up to highly efficient 64 QAM. It's literally the difference between driving on a bumpy dirt road and cruising on a multi-lane highway. When CQI is high, coding efficiency skyrockets, and your users get those rapid, seamless speeds they expect.
Moving on to Section 2, reporting mechanisms. The network can really only optimize what it can accurately see, which brings us to how these report cards are actually delivered.
So the user equipment generally has two main ways to report its CQI. First, you have periodic reporting sent at regular, scheduled intervals via the PUCH control channel. And then you have aperiodic reporting, which is specifically triggered by the E node B and sent via the push data channel. What's absolutely crucial to remember here is that aperiodic reports always take priority. If both are scheduled at the exact same time, no question, the device drops the periodic report and only sends the aperiodic one.
Now, to get even more granular, this reporting comes in 3 distinct levels. You've got wideband, which is just one broad summary value for the entire downlink bandwidth. Then there's the UE selected subband, or the best M average, where the device reports a wideband CQI plus the average of M preferred subbands. And finally, the higher layer configured subband, also known as full feedback. This is the most detailed level. It literally breaks down the channel quality across every single physical resource block. It's essentially like switching from a blurry overview to a high-definition microscope.
Right, on to Section 3, key monitoring metrics. Because before we start messing with any parameters, we need to know how to properly identify a sick cell by checking its vitals.
The absolute most crucial point here is this specific threshold, 20%. According to optimization guidelines, if more than 20% of a cell's sampled CQI reports come back as a 6 or lower, well, you have a defined problem cell on your hands. That's your red flag. It means way too many users are stuck down in that inefficient QPSK modulation we talked about earlier.
But a bad CQI score alone doesn't tell you exactly why the cell is sick. To confirm if that poor CQI is caused by heavy downlink interference or just plain weak coverage, you have to cross-reference it. You want to look at the RLC layer downlink average throughput. You need to check push MCS and push CNIR. And finally, review the UE power headroom. Because if a phone is shouting at maximum power and still getting a bad connection, you know for sure you're dealing with a fundamental coverage gap.
That brings us to Section 4, our 5 pillars of optimization. We have our diagnosis, we understand our metrics, so let's prescribe the cure.
We're going to structure our optimization exactly how an experienced RF engineer approaches a site. First, we start physical with the RF environment, then adjust power control, optimize scheduling mechanisms, fine-tune MIMO and transmission modes, and finally, implement RSRQ mobility logic.
Pillar 1 is purely physical, RF environment optimization. Before touching the software, you absolutely have to look at the hardware. This means physically adjusting antenna tilts, azimuths, and heights to resolve weak coverage blind spots, while simultaneously minimizing overlapping or cross-coverage interference. If you have two towers blasting the exact same area, your CQI is going to tank every time due to the resulting co-channel interference.
Next up is Pillar 2, Power Control. When handling interference, the approach here might actually surprise you. If a cell suffers from high interference, you want to explicitly disable reference signal, or RS, boosting. By turning this off, you essentially mimic a de-boosting effect, which can significantly clear up the noise floor. Additionally, you should enable PDCCH power control. This gives the network far more flexible power scaling without being forced into higher, way less efficient aggregation levels.
Moving right along to Pillar 3, Scheduling Mechanisms. Field tests give us some very specific parameters here, explicitly enabling aperiodic reporting by setting CQI APER enabled to true, setting the algorithm mode to FBT2, finding the best balance for subband cycling with CQI peer SB psych at 4, and this is a big one, switching the periodic feedback type to UE selected. Making these adjustments provides a massive, super reliable boost to overall network performance, simply because it ensures the network is acting on the most relevant, timely data possible.
Now, Pillar 4 dives into MIMO optimization and transmission modes. Transmission Mode 3, or TM3, tries to keep data flowing in dual stream for maximum speed, provided the CQI and rank indicator are high enough. But if they drop below a certain safety threshold, the network falls back to a much slower single stream. So the optimization goal here is actually a bit counterintuitive. We want to deliberately lower those safety fallback thresholds to keep devices locked into dual-stream transmission for much longer.
To actually achieve this, we aggressively drop 4 specific MIMO parameters. We lower the CQI upper limit from an 8 down to a 2, and the CQI fallback limit from a 7 down to a 1. We also lower the rank indicator upper limit from 1.6 to 1.2, and its fallback limit from 1.4 down to 1.1. By dropping these defaults, you effectively trick the network into staying in dual stream. In actual real-world test sites, engineers saw a 2% overall jump in dual stream usage. That boosted average speeds for poor signal users from 25.6 up to 27.8 megabits per second. That is a highly noticeable, very real difference for the end user.
Also, while we're on MIMO optimization, we have to balance Transmission Mode 3 versus Transmission Mode 4. TM3 is open loop, which makes it the absolute champion for users in high mobility situations, like someone driving down the highway. But TM4 is closed loop. Thanks to pre-coding gains, TM4 provides far better performance in SINAR for stationary users, particularly those who are stuck out on the mid to poor edges of the cell coverage. And our fifth and final pillar is RSRQ mobility. Basically, this is prescribing a handover to an entirely different cell if the current cell's signal quality degrades too far. By utilizing RSRQ-based cell reselection and handovers, you're proactively pushing user equipment that is experiencing poor signal over to better neighboring cells way before their connection drops completely.
All right, final section, real-world success cases. Let's look at how these pillars actually hold up when engineering teams put them into practice, on the ground. The Shanxi Unicom project is a textbook example of this working. When they enabled and tuned RSRQ mobility, the results were totally undeniable. They effectively reduced the proportion of poor CQI in the primary cell. They saw huge improvements in RSC setup success rates and lowered their drop rates across the board. Now, a quick note on this. Handover volume did naturally increase, which means you really have to be careful with your threshold tuning. But overall, it proved without a doubt that RSRQ mobility is a highly effective standard optimization tool. Ultimately, optimizing CQI is a constant, ongoing balancing act between signal quality and sheer network capacity. It's a discipline you have to stay on top of. So I want to leave you with this final thought to take back to your own engineering teams. When was the very last time you audited your network's reporting parameters? Fixing these hidden inefficiencies could literally be the key to unlocking the true speed of your LTE network. Thanks for joining us for this explainer, and we'll see you next time.